Okay, so yeah, let me define. Let me define a sheaf homomorphism. um, so so definition. So a sheaf homomorphism alpha. Yeah. So X is topological space. And the F and Y sheaves of abelian groups. Sheaves of abelian groups. Then a sheaf homomorphism alpha from F to Y is a family of group homomorphisms, is a family of homomorphisms homomorphisms alpha u in f of u where u is open, is a family of homomorphisms such that that are compatible with the restriction homomorphisms. Such that this diagram is commutative. So that we have f of u f y of u alpha u. Then here we have f of v y of v, and this is the restriction homomorphism u v. And let's see, u v. Ну, как бы, эти слои же, как бы, они так вот отделены друг от друга, но как надо же все-таки, если просто на слоях определять, уж больно много их-то получится, да? Все-таки надо, чтобы они как-то склеивались, да? Ну, то есть вот мы же хотим там. Вот. Ну да. Да. Вот. Ну, игра со слоями, она как раз будет, да, то есть какие-то свойства гомоморфизмов как раз и будут проверяться, ну, да, свойствами на слоях, да. Но все-таки сами гомоморфизм определяется даже на сечениях. So, such that, this diagram is commutative, that this composition is equal to this composition, meaning that alpha u composition rho u v is equal to rho u v composition alpha v. Here of course u we consider some subset, two open subsets such that v is included in u. Okay. Yes. So this simple definition. First remark is that we will often omit writing this u in this homomorphism. So some remark. We will often omit u in alpha u. Meaning that we will write f of u alpha y of u. Okay. Yes. Yeah, and then natural what are use examples that we will actually use. Yeah, so examples. Examples. Yeah. Yeah. For example. Yeah. So suppose x is a Riemann surface. Then, so we have a natural. We have an inclusion. An inclusion, for example, yeah, holomorphic functions in meromorphic functions. Yeah. So this gives a sheaf homomorphism. So this gives a sheaf homomorphism from O to M. Yeah, just given just by this natural inclusion. Yeah, and analogously we have analogously. Yeah, we have yes, sheaf homomorphisms. Given by inclusion, yeah, for example, yeah, for example, yeah, locally constant functions in holomorphic functions on a Riemann surface, or for example, continuous functions in smooth functions on a manifold. Yeah, so by this, this is the sheaf of continuous functions, and this is the sheaf of smooth functions. Yes, yeah, there is a a bit more interesting example. Suppose we consider a manifold. Yeah, then the continuous functions, smooth function. See, this is locally constant functions with values in C. So, as I told you, yeah, this is often denoted just by the letter, just by the symbol of the group. Yeah, manifold. Then taking the differential D of a smooth K form gives a sheaf homomorphism sheaf homomorphism D from the sheaf of smooth K forms to the sheaf of smooth K plus 1 forms. Ой, да, слушайте, что-то глупость, да. Конечно, да. Да, конечно, да. Гладкие являются непрерывными. Of course. So we have an inclusion of smooth functions in continuous functions. Yes. yeah, so taking the differential, we can take the differential, so this gives a sheaf homomorphism. Yeah, I don't write it, but okay. So yeah, sometimes of course it's important to understand what kind of sheaves we consider. So we usually define sheaves of abelian groups, but yeah, of course, yeah, and I mean it's important to understand what kind of homomorphism it is. Yeah, so here we define a homomorphism of sheaves of abelian groups. Yeah, and these are sheaves of vector spaces. Yeah, and this is a sheaf homomorphism of vector spaces, yeah, which is defined in the same way. Okay. Okay. Then another useful example is the following. So so consider Riemann surface, and then define for f in for a holomorphic function on some open set, define define x f, just the exponent of 2 pi I f in O star of u. And this defines a sheaf homomorphism from O to O star. So this defines a sheaf homomorphism from a sheaf homomorphism X from O to O star. Yes. Yeah, I mean, probably just for maybe a bit cosmetic reasons, because we will consider this this sheaf homomorphism is a part of okay. So for this sheaf homomorphism, one can consider its kernel. Yeah, and then the kernel, I will define it in a minute, is exactly then the sheaf of locally constant functions with values in Z. Yeah. So yeah, yeah. Of course, I mean it's the same, but otherwise, just formally I could not write that the kernel is Z. Yeah, I will have to say it's 2 pi I Z, but okay. So we will have a short exact sequence. Yeah, actually it's important short exact sequence, which is actually used quite often. This one. Yes, but yeah, we will define these this in a minute. Yes. So okay. Yes, and then yes, and then yes. Again, then now we would like to consider the kernel of a sheaf homomorphism. So suppose X is a topological space, and alpha, and yeah, F and Fy abelian group, sheaves of abelian groups, sheaves of abelian groups. And alpha is from F to Y sheaf homomorphism. Yeah, then we can define the kernel. Yeah, so we can define KU, the kernel the kernel FU to YU alpha, where U X open set. Yes. Yeah. Then clearly, if we have some subset of U, then rho U V yeah, so if V is inside U, so we have F of U, F of V, the restriction homomorphism. And then rho U of K U is inside K of V, Ka of V. Yes. So clearly this defines a pre-sheaf clearly. The sets, the groups KU with restriction homomorphisms rho UV form a pre-sheaf. Yeah, this is obvious, but yeah, now the next simple lemma says that this is a sheaf. This is a sheaf, so the kernel is a sheaf. For a pre-sheaf, and the pre-sheaf denoted by K equals kernel of alpha. Yeah, this is the kernel. And then the lemma says that K alpha is a sheaf. Yeah, it's and the proof is the following. Okay, so let us check sheaf axiom. Sheaf axiom 1. sheaf axiom 1. So we have U is the union UI. Yes, yeah, and then and then F G are in KU. Yeah, and then we know that F restricted to UI is equal to G restricted to UI. Yeah, but okay. So F and G are from K of U, but this is a subset in FU, subgroup of FU. Yes. Yeah, but then of course, but then this implies that F is equal to G by sheaf axiom 1 for applied for the sheaf F. Yeah. Because elements of the kernel are elements of the sheaf F of U. So so sheaf F sheaf axiom 1 for this kernel is obvious. Yeah, then sheaf axiom 2. Okay, again, U is equal to the union UI, and then we have Fi. Fi GI. Sorry, Fi belongs to KUI, and we know that Fi restricted to UI J is equal to Fj. Okay. Yes. Okay. So again, K of UI is a subgroup in F UI, and then we can apply. So since these guys are elements of F of UI, we can apply sheaf axiom 2 for the sheaf F. So by sheaf axiom 2 for F, there is F in F of U such that F restricted to UI is equal to Fi. So we have to check. That F belongs to KU. Yes, which is equivalent to the fact that alpha applied to F is equal to 0. Yes. Yeah, so what we have FU, YU, restriction homo. Okay, and then we have F UI Y UI. But This is alpha, alpha. But alpha f restricted to ui is the same as alpha of f restricted to ui. So this is alpha fi, and this is 0 because we took fi from k of ui, so this is 0. So by sheaf axiom 1 for y, we get that alpha f is 0. Yes, so this is the proof. Yeah, so we yes. Okay, are there any questions about this? Okay, if there are no questions, then probably, since we have an exercise class, there should be problems, some problems for discussion. Then a good problem is to show that for the image it's not true. So the kernel is the kernel of a sheaf homomorphism is a sheaf, but the image of a sheaf homomorphism is not a sheaf. So I suggest to construct an example. Okay, and let me formulate it. Just write what I said. X topological space. And f again, alpha from f to y sheaf homomorphism. Then we can define B bu as the image fu to yu. Yes, then yeah, again I write f of u y u then so this is restriction homomorphism. Then rho u v b u is inside b of v. So this means that the image, so these subgroups, they form a presheaf. So that B is a presheaf. And but so problems show that in general this is not a sheaf. That in general B is not a sheaf. So the image is not necessarily a sheaf. Yeah, actually, yeah. So, yeah. Maybe. So you want to go and try? Huh? Yes, yes, you're right. It works. So you can go and try and check it. Mm-hmm. Ah.
I believe like fun in this thing, but okay. Okay, so I don't know if they could hear me, but anyways, we have this homomorphism. Yeah, I guess it's clear that this is homomorphism.
Yeah, we actually defined it.
Yeah. Okay. Then again we have for x the complement of 0 in the complex line, and well, what can we definitely say that for small enough. Okay, I guess I will not do this. So we have z. It is defined globally. Yeah, and well, there is a covering such that for each alpha, the restriction of z to u alpha belongs to the image of the exponent. That is more or less clear, I believe, yeah?
Yeah, you explained it last time that around, so if we take indeed complex plane, that indeed without zero, that indeed around any point except zero, there's a logarithm of z, correctly defined. And this means that.
Oh yeah, basically because exponent is a local isomorphism, yeah. So
Ну да, то есть он локально вокруг каждой точки логарифм существует, логарифм корректно определен. Ну, мы его выбираем конкретно для z.
okay.
Говоря, покрытие, оно, мы так говорим, конечно, достаточно маленькое, а можно просто взять два множества.
Okay, so yeah. And then if the image of the sheaf of homomorphic function was a sheaf, then we could glue up all these functions to a function from the sheaf, from the image. Well, there is only one function to which all of these glue up, being z, the identity function. So if exponent of O is a sheaf, then z is equal to exponent of some function h. Which is not the case, as we proved in the last time, I believe, or the one. So that's a contradiction, which implies that the exponent of the sheaf of homomorphic function is not a sheaf. I'm not sure if anyone could see what I'm writing, but I kind of said it out loud, so I believe it's clear. Ну как? Нет, z это не какая-то функция, z это просто функция, это тождественная функция в смысле. Вот. Ну, если мы взяли тождественную функцию, ограничили ее на элементы покрытия. Нужна какая-то функция, которая при ограничении элементов покрытия тождественная. Ну, выборов немного, это может быть только тождественная функция, правда? Вот. Нужна тождественная функция, это экспонента, потому что, ну, вот мы задали так гоморфизм наш к экспоненту.
Если мы предполагаем, что образ это пучок, да, то z должна быть в образе, то есть должна быть экспонент какой-то функции. why no? I mean,
А если взять все, то z не лежит в звездочках, потому что там не обратим.
Ну да, но здесь мы как бы, то есть надо взять что-то, не знаю, это вы проходили или нет, насчет того, когда существует логарифм, да, то есть надо взять что-то неодносвязанное, да, то есть если у нас односвязанная область, то на ней всегда логарифм определен, как бы, то есть тогда образ будет пучком. Ну да, образ как бы будет все функции. Вот. То есть мы должны какую-то взять область, которая не односвязана. Тогда там можно какую-то функцию придумать, которая не лежит в образе экспоненты. Вот. Okay, so if there are no further questions, then some examples of kernels. Natural examples. So, examples. Of kernels. Yeah, for example, so the kernel of the homomorphism from O to O star we denote it by X, EX, is exactly the sheaf of locally constant functions with values in Z. Yeah, this is because e to the power exponent to the 2 pi I 2 pi I Z is equal to 1 is if and only if Z is an integer. Что? Не очень. Ну, так поэтому мы и определили это же. Ну, мы на лекции сказали, что когда я пишу, когда я говорю про пучки, то z обозначает пучок локально постоянных функций. То есть действительно он может быть значения разные. Да? Again, sometimes I see it sometimes confuses somebody that, we denoted by this symbol the sheaf of locally constant functions on X with values in Z. Подчеркивают? Ну, да, я понимаю, да. Но просто я же говорю, основной источник у нас это группа книжка Форстера, а там как бы не подчеркивают, там просто. Поэтому я так все-таки стараюсь значение исследовать как бы этой книжки. Вот. Да, логичнее было все-таки чуть-чуть видоизменить, это правда. Okay, so yes, another important example. We can consider this differential map from smooth. So if we consider a manifold, then we have sheaf homomorphism given by differential from smooth functions to smooth differential to smooth forms. And then the kernel, we know that the differential is 0 if and only if it's a locally constant function. So it is equal to C. Mhm. Okay. Okay. Yes. Then, okay. These are two examples that will be useful. Okay, and then there is a notion of exact sequence of sheaves. So, again, if X is a topological space and alpha F sheaf homomorphism, then we have the induced homomorphism of stalks. We have the induced on the stalks. On the stalks, we denoted by alpha x from fx to yx for any point of our topological space. M, again, smooth manifold. Yeah, probably I have to say it, yeah. Since at the beginning I said that for us a manifold is a topological manifold. Okay. Ну так там же нет понятия гладкие функции, да? Ну это я так, как бы, это уже казуистика. Это просто я в самом начале курса сказал, что когда буду говорить многообразие, я понимаю топологическое многообразие. Это все, конечно, не очень важно. Это понятно, о чем идет речь. Okay. Yes, so we have the induced homomorphism of stalks defined on representatives. Okay, and then okay, defined as follows. As follows. So so if we have some element, of the stalk, then F is represented by, so the stalk is the a set of equivalence classes, so we can take a representative, and a representative if some is some section, then F is represented by F tilde in Fu, where U is a neighborhood of X. Yes, and then alpha X of F is the equivalence class of alpha F tilde from Y of U. Yeah. Okay. Yeah. Okay. And then obvious. I mean, standard arguments show that this doesn't depend on the choice of the representative. And then this is homomorphism of group homomorphism. Okay. Yeah. And then yeah. And then the definition uh, um, a sequence of sheaf homomorphisms f1 fn is called, this is denoted by alpha 1, alpha 2, alpha n minus 1, is called exact if the sequence group homomorphisms f1x alpha 1x f2x alpha 2x fnx is exact for any point is exact for any x sequence of group homomorphisms. Yeah, and by exact sequence of group homomorphisms, I mean, of course, that the image of alpha I x is equal to the kernel of alpha I plus 1 x for I greater or equal to 1 less or equal to n minus 1. Yes. Yes. So you see that this definition is probably not immediately obvious because yeah, probably if one if one sees the definition of sheaf and of a sheaf homomorphism, one can probably expect that if you want to define a sheaf as an exact sequence of sheaf homomorphisms, then we should say that this sequence should be there should be I mean that the sequence of yeah, probably one should expect that one should say that this sequence is exact, yeah, for any open set. But this is not correct definition. This is and the correct definition is to define an exact sequence of sheaf homomorphisms using stalks. Yes. Yeah. Any questions about this definition? Okay. Ну, вот, ну да, да, не, ну да, кстати, да, да, то есть можно действительно эквивалентно сказать, да, используя пучковизации, да, я думаю, это будет правда, да. Ну, будет просто такое длинное определение, надо еще эти просто определение пучковизации, оно такое тоже, ну, довольно формальное определение, все-таки так, мне кажется, понятнее. Okay, and then yes, and then yeah, and then a short exact sequence is as usual. So a short exact sequence is an exact sequence of the form 0 some sheaf f y 0. Okay, yes, and then what are again useful examples? Yeah, again, examples. Again, our favorite example. So 0 z o star yeah, 0 is a short exact sequence. Is a short exact sequence. Yes. Yes. So yeah. Okay. And that maybe just maybe we should think about it. I mean, it's not hard, but it's easy. But okay. Let us probably say some arguments. So it is a short exact sequence, meaning that this sequence OX O star X is exact. Is exact. Yes. Okay. 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 So what we have to prove? So we have to prove that this this is inclusion. Yeah, injective. And this is surjective. This is surjective. Yeah, the fact that this is surjective. Okay, so we actually more or less used many times. Yeah, that this is again the fact that if a function is not 0 at some point, then locally there exists a logarithm. Yeah. So if we have some, so because an element here is some function defined on a small neighborhood of x. Yes, and okay, this function is not 0 at this point. And then okay, if we have sufficiently small neighborhood, then there exists a logarithm of this function. Yeah, and then okay, then it means that it belongs to the image of this map X. Okay, yeah, and then here I mean the fact that it's injective is also, so these are just locally constant functions and these are holomorphic functions. Of course, I mean this is an inclusion. Yeah? Okay, and then here we have to check the exactness here. Okay, so we already mentioned that. Yeah, so I already mentioned that Z is the kernel of this sheaf homomorphism. Yeah, so obviously then the image of Zx belongs to the kernel of this X. Yes. Okay, then, I mean, this is obvious. I think that the sequence is exact at this point, yeah? I mean, обратное? Ну, как бы, ну да, здесь, если подумать, здесь все более-менее очевидно, да? Да. Ну, потому что, да, ну, вот взяли росток функции, да, вот его экспонента равна единичке, да, ну, значит, значит, это росток функции, значит, функция определена какой-то в окрестности x. Ну, вот, ее экспонент равна единичке, значит, эта функция принимает значение, ну да, в целых числах, значит, она в образе есть, да. Вот, ну да, so, okay, so. Okay, so yeah, so it's basically obvious. The only more or less non-trivial fact that is used here is that I mean the logarithm. There is one can also always take logarithm of a function in a small neighborhood of a point where this function is not zero. So yeah. Okay, I see that. Okay, so this is an important short exact sequence. Yeah, another standard thing, short exact sequence that is used, that is often used, is the following. So we can take 0, C, then so we consider a manifold, and then we can take 0, C, smooth functions, and then take the differential and map it to smooth one forms, then again smooth two forms, and etc. And so this is an exact sequence. Is an exact sequence. Huh? Sorry?
The complexification kills all the cohomologies.
Но это же лемма Пуанкаре, то есть локально. То есть нам нужно доказать, что локально каждая замкнутая форма точная, да. Вы хотели взять как бы сечение, да, и как бы получается гомологидерама, да. Is an exact sequence. Yeah. So this is equivalent to. This is of course non-trivial fact, but I hope you studied it in the course about analysis on manifolds. Yeah. So that epsilon x is exact. But this follows from I think it's called Poincare lemma, yeah? Huh? Yeah. Poincare, yeah, it's of course non-trivial fact, but yeah, some standard fact. So Poincare lemma that any closed K-form, smooth K-form, is locally exact. Yeah. Ну да. Первый будет ядро, ну да. Ну да, это мы, кстати, сейчас будет такая лемма, да, в принципе. Хороший вопрос, да. Ну, хороший вопрос. Да, у нас как раз будет лемма, из которой это сразу следует. Да, формально говорят, надо проверять. Okay, so are there any questions about these examples? Yes. Okay, if there are no questions, then we continue. Okay, probably, yes, since okay, so since there was this question, probably let me immediately okay. Let us let us prove the following simple lemma, saying that if the sequence 0 f alpha is exact, so is exact, then yeah, it is exact for any then 0 f u is exact for any open u, for any open u. Proof, yeah, so we have to check that it's injective, so have to check that fu is injective. Okay, so ну да. Ну да, просто дело в том, что я хотел как бы, вы можете, если вам очевидно, для тех, кто очевидно, могут сразу подумать над задачей, что это неверно если наоборот написать, то есть okay, maybe here I explain the proof, but for those who thinks this is да, ну тут можно еще дополнить чуть-чуть следующим, да, то есть so problem that if the sequence f 0 is exact, then this doesn't imply that this is exact. So you can think about it. I mean, for those who find it obvious, clear. We have to check that it's injective. Okay, so suppose you take here some element f. So suppose alpha f is 0, then yeah, then yeah, so then alpha f, then of course alpha the germ of alpha f is 0, but yeah, the germ of alpha f is the same as alpha of the germ of f. Yes, but then so we know that the germ of f is 0, and we know that this sequence is exact, meaning that it's exact on stalks. Then this means that rho xf is 0 for any x on our topological space X. Yeah, but then we had this lemma, yeah, that this implies that f is 0. Yeah, at the very beginning we had a simple lemma saying that yeah, a section of a sheaf is 0 if and only if all the all its germs are 0. Yeah. So yes. Then okay. Are there any questions about this?
Is it right that if we add an arrow to the 0, it will still be correct?
I mean, you want an arrow, one more arrow here? Here? Yes, yes. Yes, yes. Yes. I mean, I don't know. Yeah, maybe our next statement will be about this. But okay, what about this problem? So the problem says that yeah, if you write in the opposite direction, then it's not true. Who can explain that? Sorry? Yes, yes. Yes, always one the same example. Okay, the same example. Yeah, O 0. Yeah. Yeah. So yeah. So actually we yeah. Any questions about this? Okay. Okay. And then indeed actually there is another statement saying that if 0 f y h is exact, then 0 f u u is exact for any open set u, is exact for any open set u. Yes, so yeah, and the proof is the following. So here let us do alpha and beta. Alpha and beta. We already proved in the previous lemma the exactness at this term, so we only have to prove the exactness here. So have to prove that that image alpha is equal to the kernel beta. Yeah, okay. I mean, the first is simpler, that the image alpha belongs to the kernel beta. yeah, for this we so we take some element here. Yeah, then of course we take the composition. Yeah, so we take alpha f but so we have to check that this is 0. Yeah. Okay, but then again, you check for germs. Yeah, so you take rho x of this guy, and this is the same as alpha x, rho x. So the germ of the composition is the same as the composition applied to the germ. Yeah. But this is 0 because the sequence is exact on stalks. Yeah. 0. Yeah, but yeah, again, the first lemma of the lecture gives that yes, so what I wanted to say. Yeah, so this element, the germs of this element at every point are 0, so this implies that beta alpha f equals 0. Yeah, and so this implies that image alpha is in the kernel of beta. Okay, a bit more now. Let us do a bit more interesting part. That the kernel of beta is inside the image of alpha. Yeah. So what we do? What we do? Okay. Yes. Okay. So we have 0 f u y u h u. Here we take some element g. Yes. And it goes to 0. It goes to 0. Yes. So, yeah. So alpha, beta. So we see that beta. So we go to germs. So beta x of the germ of G is 0. So this implies that the germ, yes, by the exactness on stalks, that the germ of G is in the image in the image of alpha x. Yes. So there is an open neighborhood neighborhood ux of x such that such that G restricted to ux is alpha of some fx for some fx in f of ux. Yes. Yes. So then we look at the intersections. Yeah. So we have. Yeah. So then. So U, we see that U, our set U, is the union over all x in U or ux. Ux. Yeah, G restricted to ux is alpha of fx. Then we have that alpha of so on the intersection on ux intersected with uy, we have that alpha fx minus fy is what? Is g restricted to ux uy minus g restricted to ux uy. So this is 0. Yeah. So since yes, and then so you see that alpha of this difference on this intersection is 0. So by the previous lemma, we conclude that fx minus fy on probably better fx restricted to ux uy minus fy y. By the previous lemma we have that, yeah, probably it's better to write like this. Minus fy restricted to is 0. Yes. But then this implies that there is f on f of u such that f restricted to ux is equal to fx. Yes. Yes. Yeah, and then alpha applied to f restricted to ux is equal to alpha of f restricted to ux. This is alpha of fx. Yeah, and alpha of fx as we is g restricted to ux. Yeah. So you see that alpha f restricted to x is the same as g restricted to ux. So this means that alpha f is equal to g. Yes. So this implies that the kernel B is inside the image alpha. Yeah, as required. Yes. Yeah. Are there any questions about this? Okay, if there are no questions, then we should finish. So yeah, in the evening I will send you homework